Swayam Prabha. Digital India. Educated India.
Okay, so let us continue our discussion on the phase plane analysis of second order systems. In the previous lecture, we took the example where the eigenvalues were real, and we took 3 cases where we had lambda 1 and lambda 2 both positive, lambda 1 and lambda 2 both negative, and in the third case one of them was positive, the other one was negative. So, as a quick reminder, we are looking at higher order systems which can be expressed in this particular form, and the solution was given as x bar is equal to summation C I e to the power lambda I t V I bar, where lambda I are the eigenvalues and V i's are the corresponding eigenvectors. Now, let us look into a particular form of the matrix A, where so we have case 2. Okay. So, we have A which is given as 0 B minus B 0. Okay. The eigenvalues which we considered in the previous lecture were all positive, were all real numbers, they were not imaginary numbers. But if you solve for eigenvalues and eigenvectors for this particular case, what you will find is that lambda 1 is going to be I b and lambda 2 is going to be minus I b. They are going to be imaginary numbers. Okay. And the corresponding eigenvector, so let us take one of them e to the power I b. The eigenvector for e to the power I b can be determined as 1 I. Okay. And therefore, what you can do is that you can write the solution as x 1 x 2 is equal to e to the power I b t multiplied by 1 I. The solutions would be linear combinations of both the terms. We are considering for the time being only one of the terms to understand the behavior of the system. Okay. This is the solution, and what I will then do is I will convert e to the power I b t like this, e to the power I b t is equal to cos b t plus I sin b t. Okay. So, I get x 1 x 2 is equal to cos b t plus I sin b t multiplied by the vector 1 I, which is going to be equal to cos b t plus I sin b t multiplied by minus sin b t plus I cos b t. Okay. This is x 1 x 2. I can further simplify this as cos b t minus sin b t plus I times sin b t cos b t. So, what you see here is that I have solutions which are complex numbers. So, I can write this as real part of the solution plus imaginary part of the solution multiplied by I. And it is not very difficult to show this by simple substitution, that the real part is a solution and the imaginary part is a solution individually. So, if you substitute this real part in dx bar by dt is equal to a 0 b minus b 0 x 1 x 2, then you will see that you will get this this part satisfies this equation and this part also satisfies the equation. Okay. So, if that be the case, I have solution 1, I have solution 1 and I have solution 2. Okay. So, let me do one thing, let me write this here, solution 1 as cos b t minus sin b t and sin b t cos b t. So, cos b t minus sin b t and sin b t cos b t. Okay. So, V 2 is a solution and V 1 is also a solution. If V 1 and V 2 are individually solutions of my linear system, then I know that their linear combination would be also a solution. So, I can write the ultimate solution of my system as C 1 times cos b t minus sin b t plus C 2 sin b t cos b t. Let me reiterate that the reason we are writing this expression is that the system is linear, it follows the property of linearity and therefore, all linear combinations of the solutions would also be solutions. So, therefore, my solution is of this form, from where I can write x 1 x 2 is equal to C 1 cos b t plus C 2 sin b t and minus C 1 sin b t plus C 2 cos b t. And now, I would be interested in knowing the behavior of x 1 and x 2 when they are given by this equation, right. It is a little difficult to visualize this this particular parametric plot. So, let us do one thing, let us plot it using our Desmos calculator. So, we will write this like this. So, I have C 1 cos b t plus C 2 sin b t minus C 1 sin b t plus C 2 cos b t. Okay. So, before I do some rearrangements, let me clear this up. Okay, fine. So, now what I can do is I can increase the value of b and you see what do you get? You get a circle as the solution. Let me change the values of C 1 and C 2. and let me animate it. What I see is that when I change the values of these multipliers C1 and C2, the radius of the circle changes, okay. But what does not change is the nature of the solution. What does this mean? This means that the solution has the same circular behavior irrespective of the values of C1 and C2. Okay. So, what do I learn from this? How do I draw the phase portrait? Okay. How do I draw the phase portrait? So, as I saw from the Desmos calculator, my x1 and x2 plane would look something like this. I am trying to draw it like a circle. It is not very elegant, but this is what I wanted to draw. Okay. Probably we can do something better in this part. Yeah, it is better now. Okay. So, now what I see is that I go along a circle. Remember that previously you had one solution which looked like this. In one case the values were real, in other case the solutions were like this, and in one more case the solutions were like this, and so on, right. But the values never repeated. What is the meaning of this? What is the direction of time now? Okay. Now, the question is, what is the direction of time? You have, if I animate this with respect to B, you will realize that now you see the direction of time. You can see the circle evolving in time. So, depending upon the parameter B in your case, you either have clockwise or anti-clockwise evolution in time. But in any case, once the system has completed a circle, the system keeps on revolving either in counterclockwise direction or clockwise direction. So, that means that the value. So, for example, if I am here at some point of time t. So, I will have some value of x 1 and some value of x 2. When the system completes this circle, which means after one period of this circulation is over, my value will again be the same, right. That means the system has repetitions. This repetition was not observed here, this repetition was never observed here, this repetition was never observed here. But when the eigenvalues are purely imaginary, this is important, purely imaginary, not just complex numbers. When the eigenvalues are purely imaginary, then what you see is that you have a dynamical behavior which looks like this, and therefore, such solutions are called center solutions, because about a center the solutions keep revolving, and this happens. This is a typical behavior when you have a system where the eigenvalues are given as purely imaginary numbers. Now, imagine that you have a system where A, which was initially given as 0 B minus B 0, is given now as A B minus B A. So, the diagonal elements which were previously 0 now are now A. In this case, the eigenvalues become a plus or minus I b, and lambda 2 becomes a plus I b, and lambda 2 becomes a minus I b, right. So, in the previous case you had the eigenvalues which were purely imaginary. Now, you have complex numbers, okay. A cannot be 0. So, let me emphasize that a not equal to 0. So, what is going to happen to the solution? The solution would be something like this. Let us consider the first case, the eigenvector is the same, which is 1 I. Please work out yourself to convince yourself that this is the eigenvector that you would get. So, what you are going to get is this x 1 x 2 is equal to e to the power eigenvalue, which means a plus I b times t multiplied by 1 I, right. So, I will write this as E a plus I b is equal to e to the power whole multiplied by t is equal to e to the power a t multiplied by e to the power I b t, right. So, now what has happened, all that has happened is that your solution has now been multiplied by e to the power a t. So, e to the power I b t remains the same, right, and then you will multiply here and carry on with the exact same steps. So, therefore, what is going to happen is that my ultimate solution x 1 x 2 is going to look like this: e to the power a t cos b t minus sin b t. This is the previous solution which I got, e to the power a t cos b t plus sin b t, right. Cos b t plus sin b t minus sin b t cos b t. Okay, so, this has to be corrected, cos b t plus sin b t. So, this has to be plus sin b t and minus sin b t minus sin b t plus cos b t, fine. And what has happened in this case is that the entire term has been simply multiplied by e to the power a t. But what is the effect of multiplication of e to the power a t to this circular behavior? If I consider only this behavior, which was the previous solution, if I consider only this behavior, the previous solution, my behavior was like this: x 1 x 2 and I have a center solution, right. Depending upon the value of b, you would have one or the other direction of the arrow. But now I have multiplied this effect, this circular effect, by e to the power a t. Now, what is the behavior of e to the power a t? We know that e to the power a t limit t tends to infinity for a greater than 0 and it is equal to 0 for a less than 0. We know this functional form, right, which means that this circular effect, the effect of keeping the radius of the circle constant, will be augmented by the term, and the term will keep on increasing with time for a greater than 0 and the term will keep on decreasing with time, diminishing to 0 for a less than 0. Simple. So, let us see if this is the case. Let us put this here. All we need to do is we need to multiply. So, So, what we need to do is we need to multiply this by e to the power a t yes, and here also e to the power a t. Let us see what happens here. Clearly, without doing anything, you saw that there is no more a circle of constant radius, right. But what has the software done is that it has assumed a value of a is equal to 1, which means a is greater than 0. So, that means you started from here, and instead of reaching a constant value, so this would have been your constant radius circle roughly, you started diverging, okay. And let me increase the time. So, I can increase the time by doing something like this. So, let me do it. See here. So, I can do one thing from 0 to say 100, okay. And if when I increase the time, remember that my value of a is greater than 0, and what I see is that I keep evolving. So, let me show that the system in fact diverges from the initial value to a larger value. What happens when the value of a is less than 0? You see here. So, let me again make the system evolve with time. This is how the system is evolving with time. It is tending to 0 asymptotically. Okay. So, as I increase the time, the value of my x and y asymptotically tend towards 0. So, therefore, now I have 3 types of phase portraits. x1, x2, x1, x2, x1, x2. The first portrait was this when lambda was a plus I b with a is equal to 0, right. This is the center solution. This is the center solution. Okay. Now, I have lambda is equal to a plus I b with a greater than 0. This is important, a greater than 0. So, I start with some point and then as time increases I tend towards infinity. So, what should I call such solutions? These are called spiral. Why spiral? Because you get a spiral, right, spiral source. And in contrast, when lambda is a plus I b, when a is less than 0, you start with a point and then you spiral down towards 0, and this is spiral, this would be spiral, but spiral sink. So, let us very quickly draw all the possibilities which we saw today. x1, x 2, x 1, x 2, now case 1 when lambda 1 and lambda 2 are real, lambda 1 and lambda 2 are real and lambda 1 is less than 0, lambda 2 is greater than 0. Okay. So, what you get is a saddle solution, you get a saddle solution. Okay. Since lambda 2 is greater than 0, you would have the second axis as the divergent axis and therefore, this would be the nature of your solution. Second case, lambda 1, lambda 2 are real and lambda 1 and lambda 2 are both less than 0, both less than 0. So, depending upon whether lambda 1 is greater than 0 or lambda 2 is greater than 0, you will get one or the other directions of these curves, but in either case you would have the lines which would look like this. Okay. And this would be a sink solution. The previous solution was source. The third one, lambda 1, lambda 2 are real and both of them are greater than 0. Again, I must emphasize that depending upon the whether lambda 1 is greater or lambda 2 is greater, you will get one or the other orientations of these curves, but the direction of time would be outward, both the axes would be unstable. Now, lambda is given as a plus I b, where a is 0. Okay. So, this is okay, there is one correction, this is not a source, this is a saddle one, please note this, and this is a source solution. So, when you have lambda is of the form a plus I b, where a is 0, which means you have purely imaginary eigenvalues, then you get a center solution. Then lambda is equal to a plus I b, where a is greater than 0, your solutions look like this, and these are called spiral source, and lambda is equal to a minus I b, where a is less than 0, you get spiral sink solution. Now, finally, what we have not discussed or what we have not seen in these phase portraits is that what about the dependence of the variable or the components of the dynamical variable on time, because these plots give you the variation of one component of the dynamical variable with the other component of the dynamical variable. What if I want to know x 1 with time or x 2 with time and so on, and what is the most striking feature of second order and higher order systems is like this, that when I solve for dx by dt is equal to a x, then what I see is that my solution would either be like this or it would be like this. This is t versus x, this is t versus x, which means in either cases the solution is monotonous, right. The solutions would, the values would monotonously increase with time, as in the case here, or they would decrease with time, sorry, the other way around, they would either increase with time as in the case here, or they would decrease with time as in case here. But now, when you are solving dx bar by dt is equal to a x such that lambda for A is simply of the form I b. Then what you see is a center solution, right, x 1 x 2, and the values will repeat with the same magnitude, the values will repeat with the same magnitude over a long period of time, right. So, that means I can draw roughly the plot of t versus x 1, for example, like this, because these values are the same, the magnitudes are the same. So, a center solution would correspond to this non-monotonous behavior. This behavior is non-monotonous, which you will never find in first order systems. And finally, when you have spiral source or spiral sink solutions, this is spiral sink for example, if I want to correspondingly draw t versus x 1, this is x 1 and x 2, at any given point of time, what is going to happen is that my magnitude is decreasing. So, therefore, I can say that I have a behavior which is like this, where the magnitude, the amplitudes are decreasing. Conversely, what you can also have for the spiral source is this, that at any given time the amplitude is increasing. So, therefore, you may have a system which behaves like this, that the amplitude of your system is actually increasing with time. So, we saw how the eigenvalues of the system govern the dynamical behavior of the system, whether the eigenvalues are positive or negative, whether the eigenvalues are real or imaginary, or whether the real part of the eigenvalues is positive or negative, will determine the future behavior or the dynamical behavior of the system, whether the system would be convergent or divergent, whether the system would change monotonically or it would oscillate, whether the oscillations would be sustained oscillations or they would die out with time, or they would increase in amplitude with time. These are all the exotic features which you would observe only in higher order systems, which are not observed in first order systems. So, in the next lecture we will take an example from the physical domain and see how the features that we develop today can actually be observed in real world. Thank you.